So in the first lecture, we have talked about the power of symbolic knowledge representation and reasoning for accomplishing tasks, in particular, if we want kind of the reasoning to scale in terms of generality, transferability, and being able to tackle manipulation tasks that the robot hasn't seen before. But we have also seen that kind of the representations or kind of the models we were choosing, namely the state transition model with atomic state transitions, is far too coarse-grained in order to infer kind of body motions that enable the robot to accomplish the task successfully. So the question that basically arises here, can we basically go to other kinds of models of the environment which kind of are better suited for what the robots have to do? And as you can see here, there are indeed models that that people use and that are very popular these days in order to do such things. And these are environment models in virtual reality environments. And so the question comes up, so what if we basically take that very coarse-grained representation we have in the upper right, which basically comes out of a time when computers were programmed with punch cards. So can we basically bring the representation such that it can exploit or leverage modern representation technology, right? And so what I'm talking about this in this lecture is essentially what happens if we are going and use and leverage that technology of virtual reality environments and combine it with symbolic reasoning and use it for reasoning in robotic agents. So if you compare basically that very coarse-grained representation and you see how environments are represented in virtual reality applications, it's kind of very realistic. You see essentially that you have all ways of articulation. You have very realistic geometric models. Texturing is nice, and so what we want to do is we basically want to use our atomic symbols in our knowledge representation, but now link them to subtrees in the scene graphs of virtual reality environment representations. So the idea is that we want to model the environment of the robot as a scene graph, but give the data structures in the scene graph semantics using axiomatizations and ontologies we specify using symbolic and logic-based knowledge representation. And we also wrap the virtual reality environment representation in a way that it looks from the outside as if it was a logic-based knowledge base. So if we are doing that, then we get also from our very coarse-grained model of an abstract agent interacting with an abstract environment into a modeling situation where our agents are essentially virtual reality agents, which might be a human or a robot, that are controlled by action plans, and we have access to these plans that control them. The environment is also represented as a knowledge base that encapsulates a virtual reality environment as a logic knowledge base, but also the images and the motions generated by the agents, they are basically wrapped as logical knowledge bases. Finally, we record every change in the virtual reality environment and translate it into a symbolic representation of the activity that has taken place in the virtual reality environment. And we have a knowledge representation system that you will also partly use in exercise in this fall school, which is the KnowRob knowledge representation system that is basically implementing these ideas. And I will basically talk about some aspects of this knowledge representation system. So as I've said before, so the basic idea is that we keep the symbolic representation like the predicates and the symbolic names. But now the symbolic names are not atomic entities, but they are links into the respective data structures in a virtual reality scene graph. So the milk box 23, the name is linked to the subtree of the scene graph that represents the milk box. And so what we know is in the scene graph representation, the subtree of the scene graph carries all the information that is necessary for rendering that object in a photorealistic way, but also information to simulate that object when it's grasped or when it's pushed or everything else. So this is kind of a very powerful way of representing it. So if we are looking at that representation from a knowledge representation and reasoning point of view, it's not only that we basically get a representation which is far more detailed than anything that we have seen in knowledge representation before, but it's also a knowledge representation that can be rendered as images and where we can basically take motions and simulate them in the virtual reality environment. So what that means is that we get additional inference mechanism. And we are enabling robots to reason with their eyes and with their hands, right? So if we have a symbolic knowledge base, so a robot can infer how would a situation look that satisfies these assertions, or it can also reason about what would happen if I perform this kind of boring motion in this environment. So it's extremely powerful. The other thing we want to do is we want to cast this representation as if it was a symbolic knowledge base. So this way we are getting additional logic predicates, something like expected image, which means that this is an image that the robot expects to see when it captures an image with its camera. And the way this assertion is computed is that if we are asking what is the image that the robot expects to see, the reasoning mechanism takes a rendering from the point of view of the camera pose with the optical parameters of the camera, and it generates an image. And this image is bound to the symbolic name image, right? And the robot can basically then access its expectation in the visual domain by just accessing this symbolic expression, right? We can also have other predicates, like we can have a predicate which is true for the object that kind of is at position x, y, and in the given image. This is simply computed by giving each object or object part in the scene a different color, and then we can compute which object is depicted by a particular pixel by looking up the color of this pixel, right? Or another application is that we want to basically know what is the image segment in the image that a certain object is depicted in, right? And then we implement that by asserting that all other objects besides MP23 are invisible, and then we render the image and we get a basically perfectly segmented image there. So the story is, if we have an environment representation that is a virtual reality scene graph, we can cast it as a virtual knowledge base by defining predicates that compute their truth values out of the scene graph representation of the environment. So if we are doing that, so a digital twin knowledge base consists of two components, which kind of the first one is a symbolic knowledge base, and the second one is a scene graph representation of the virtual reality environment. And of course, we want to have both knowledge bases strongly coupled to each other, which means each of the symbolic assertions in the symbolic knowledge base is true in the artificial world, and every kind of relation in the artificial world is also represented in the symbolic knowledge base. And if both representations are so strongly coupled, that allows the robot to work with representations of its environment that are symbolically accessible, but have all the information that is needed for generating motions and for interpreting images of its environment. So then, if we have the knowledge base represented as an artificial world and we execute, then we can basically look at robot control programs, and we can execute them in the artificial world, and we can execute them in the real world. So what we are doing is we let the robot execute its control program in the artificial world, but then the robot in reality acts in the real world. So it basically acts in the real world, but it thinks it's acting in the artificial world, and this is an advantage because it has perfect knowledge about the artificial world. Of course, kind of the artificial world and the real world will never be the same. So a robot control program that basically makes the assumption that the artificial world matches the real world has to be equipped heavily with event and failure detection and recovery methods. But as we will see, hopefully in the rest of that lecture, is that having that heavy machinery of event and failure detection and recovery is worth the price of getting very cool information about the world. So another thing is the question of, is it feasible at all for robot agents to have these digital twin knowledge representations of its environment? And it's feasible only if we have stories that robots can actually create these representations autonomously and that they are good enough to act in the real world. So in general, this is certainly not yet the case. But if we are going to structured and more specific domains, we can have much more progress. So here you see how a robot that is in a retail store is reconstructing a digital twin knowledge base through autonomous mapping. So what it does, it's basically detecting objects in the real world. We make the assumption that it has good enough models of all the objects and all the components of the furniture beforehand. And now it's basically reconstructing what it sees in the environment in its belief state, right? So now you see that the robot has detected the individual shelves and it basically placed them in its model. And it continues. Now it looks along the individual shelves. It identifies the barcodes and the separators. And now it knows which object has to be at each place. And now it's taking that information and tries to detect whether the objects are there or not. And that way, the robot can build a digital twin knowledge base of its environment. Of course, kind of the question whether that kind of method is also feasible in environments like apartments or kitchens, it's up to ongoing research. But if we are looking at that particular application, so what the robot has autonomously acquired as a model of its environment, it's a perfect symbolic knowledge base. So you can ask the question of kind of where is a particular product, and it's basically highlighted there. Or you can ask questions like, where are empty facings in the shelf? Or you can combine it with more comprehensive background knowledge and basically asking a query, where are items that are dangerous or life health-threatening for kids, but also at the in the reach of kids, and you would find the cleaning materials, right? So the robot control system can kind of construct these knowledge bases without manual help by programmers. So we can also basically use that information to recreate the environment as a virtual reality scene. And now, because of the rendering and physics simulation, you can go and act in the environment and go shopping. And because everything is a knowledge base, the infrastructure of the digital twin knowledge representation and reasoning system can automatically pass the fetch and place actions for shopping and kind of record them in the knowledge base. Those kinds of digital twin knowledge representations can also be used for autonomous robot manipulation. So based on the autonomously acquired environment model, the robot can then perform autonomous manipulation actions like filling a shelf. Of course, that only works for limited set of objects because of the grippers of the robot, but we also can take that technology and already build models of complete retail stores using this way. So at the moment, our best guess is that these kinds of digital twin knowledge bases can scale towards a large variety of autonomous robot applications. So essentially, as I've said earlier, is kind of a digital twin knowledge base consists of the symbolic knowledge base, the virtual reality world. The knowledge base consists of assertions and general axioms that are formalized in a logic knowledge representation, and the virtual reality scene graph, E, which enables us to render the current situation, but also to simulate the effects of motions on the world. And we have mappings from the knowledge base to the artificial world and from the artificial world to the knowledge base. So, and it's basically that kind of everything. So if we are kind of extracting the symbolic statements from the artificial world, everything that is true in the knowledge base should also be extractable by applying that function to the artificial world. And if we are taking the artificial world and we take the knowledge base and map it into an artificial world, the world resulting from that construction step should be the same as the artificial world, right? So here you see that we are taking a command in the symbolic knowledge representation, basically to reconstruct an environment based on a logic knowledge base. And you can see that the complete environment is constructed this way. So that means our symbolic knowledge base is complete with respect to the entities that are contained in the artificial world. So let us look now at how activities that are taking place in the artificial world are automatically interpreted and abstracted into symbolic representations. So here you see André, who is doing that research, performing an activity, setting the table in the virtual reality environment. You also see here the event detection that takes place in the artificial world, which essentially detects the force dynamic events, namely the hand having contact with the handle, kind of that drawer is opened, and so on. And basically detecting these force dynamic events is sufficient for automatically interpreting the activities and representing them with a grammar for manipulation actions, which reflects the model of Flanagan that we have heard about earlier. Right? And here you see that the representation that is automatically constructed already allows us to answer symbolic questions like what is the action, what is the trajectory of an object during the action. So it's already kind of extracting the semantics behind the motions, representing it explicitly using the Flanagan model, and providing it as a symbolic knowledge base. Okay. So this is very important, right? Because this gives our autonomous robots means of interpreting what's going on in the world and making sense of what they are seeing in a much more comprehensive way than what was possible for previous kind of control systems using more traditional AI methods. So that representation is then can be used through querying and inferring answering for the question. So here we basically ask the system to show an action act that is a pick and place object, and we basically want to segment that action into the sub-actions, those from the Flanagan model, which are kind of reaching, sliding, and so on. And we want to color each of these sub-actions in a different color. Important is that we essentially get the semantics in order to automatically interpret and generalize and abstract that. But at the same time, we have access to the sub-symbolic information that enables the robot to do motion learning, right? And I think that combination is kind of very important for future control systems for autonomous robots. Other mechanisms that we have talked about, right? So if you're thinking about autonomous robots that act successfully in the real world, in particular for actions that the robot has never seen in its experiences so far, it's important that the robot has mechanisms to predict what will happen when it executes new actions. So for that, mental simulation is an extremely important inference mechanisms in humans, and it's also promising to equip robot agents with these capabilities. So what we have here is that robots, concurrently with executing their actions in the real world, simulate their actions in their belief state. So on the left-hand side, the picture is actually a symbolic knowledge base, or a kind of a hybrid knowledge base with a symbolic component. And whatever is depicted in this belief state of the agent, the robot essentially understands and has knowledge in its symbolic knowledge base about. We can see that kind of the knowledge has a very high level of details. And can also see that by having that kind of belief state and simulating it, the robot can know about things that it cannot perceive using its perception system. So If it's mentally simulating its actions in its belief state, and it's basically opening the gripper, then it knows, because of the physics simulation, that the object has to drop down, right? And so again, the story is, by equipping robots and their belief state with mental simulation techniques and virtual reality simulation infrastructure, we get robot control systems that understand the world much, much better. And you see here that the activities that the robot is accomplishing in the simulation engine are very similar that we have seen in the first talk in the table setting task, which means that the model is kind of close to what the robot does in the real world. So another thing is that we do not only want to simulate what's happening in the world, but also we want to equip the robot with the perceptual capabilities of expecting what it will see. So that's important for two reasons. For one thing, if the robot has very good expectations about what it sees, it can simplify its perception tasks substantially, right? And simplifying perception tasks means making perception much more robust, but also much more efficient. So here you see that we have a kind of a scene, and now we are creating videos from the same scene from different perspectives. Can also be different kinds of cameras, and here you see different perspectives. So on the right-hand side, you see the semantics of the scene, but then you see different sensors and what they are expected to deliver. And this provides a perception system with prior knowledge that helps it to interpret images. You can also see how kind of detailed, how realistic, and how you can change essentially the images according to the parameters of the cameras. So I've also hinted in the first talk that one of the big things that we want to get is we want to have robots that can build up big knowledge bases on manipulation capabilities by themselves, right? And one way, probably one of the most promising ways of doing that is to use web pages that are made for humans and that contain instructions, written instructions, as well as videos. So what we want to do is we want to have robots that are capable of watching instruction videos and again simulate the instruction videos in their internal virtual reality worlds. So here you see a deep learning-based system that tracks the kind of body motion, and it's also detecting the objects of interest. And here you see how kind of continuous actions in the videos are aligned with symbolic expressions that describe what the system has detected in the image. Kind of, we want to do that because there are so many different ways of how to accomplish certain manipulation actions. And we know that most of them will not be feasible for robots. So it's actually very important for robots to learn about the different ways manipulation actions can be performed and to infer the ones that are feasible for them and that they can execute so that the actions will have the desirable effects. So that is done by a deep learning system that is trained on images, on videos. So for one thing, with a pose, but also for actions. And the way we want to push that technology is that we want the system to observe manipulation actions in videos, but then animate them in the digital twin knowledge bases. If we are kind of managing that, then the system could infer a lot of hidden information in videos, judge the feasibility of task-critical motion patterns and whether they are executable by the robot, and kind of how to optimize them for the body of the robot. And this is a way for us how we think we can scale robots to perform manipulation actions with any object for any purpose in every context situation. Okay, so yeah, so let me just stop here. So I think the bottom line of what I've talked about in that lecture is that if we are thinking about knowledge representation and reasoning for robot control systems, it's not necessary to think that these knowledge representation and reasoning system are limited by kind of what purely symbolic representations can do or are limited in. But kind of a very promising approach and realization that we see today is combining symbolic knowledge representation with virtual reality scene graph representations, and that the combination of both is extremely powerful. And also, if you think about our digital twin knowledge representation, you can think of all the videos that this knowledge representation system can generate as supervised training data for deep learning, right? Because in every video, you essentially have kind of the video itself, but you also have a complete representation of the semantics of what's going on. And so you can basically learn any learning tasks that you kind of imagine with respect to manipulation action by generating training data out of that infrastructure. Okay, so here I will stop. Thanks for listening.